Okay. So, as we have said, now we will try to give some interpretation on this negative frequency, the concept of negative frequency. So, let us first try to see, whenever we are saying the concept of negative frequency, what exactly we are getting. We are getting a, means as you might have seen. So, we are having this at positive frequency, we are having this mod Cn, and then some e to the power j 2 pi f0 nt into e to the power j phi n, right, or theta n. And at the negative, I have same Cn e to the power minus j 2 pi f0 nt e to the power minus j theta n. This is something we have, right. If you carefully see these two things, those two are nothing but two phasors. Okay. So, if you just ignore this mod Cn, what do we have? We have this. This is a unit length phasor in the complex plane. So, if I have, this is the real axis, this is the imaginary axis, right. So, this is just a unit length, single length phasor which is actually rotating. As I means, see here the variable is t. With respect to t, if I start increasing t, what is happening? This overall angle. So, suppose for this one, it is actually j 2 pi f0 nt plus theta n. So, theta n must be some constant, okay, which does not depend on t, and after that it is just with respect to this phasor, this particular unit thing is rotating, okay, and then only we will be getting this phasor representation, because e to the power j this one has a real part and a imaginary part. Whenever I put e to the power j this 2 pi f0, I can put as omega 0 nt plus theta n. What does this means? Actually it is cos omega 0 nt plus theta n plus j sin omega 0 nt plus theta n. Okay. We all know that if with uniform angular velocity omega 0, if we rotate a phasor, the projection to a axis along which it has a pivot along that axis, that is what is happening. The projection actually follows a sinusoidal or cosinusoidal, right. This is something we already know. So, basically what is happening, whenever I am actually rotating this with angular velocity omega 0, if I trace this projection with respect to time, I will get at the real axis a cosinusoidal and at the imaginary axis a sinusoidal. This is actually the representation in complex domain, right. So, because we are representing that as complex signal. Now, what we also know that eventually by our Fourier series representation, there was a positive frequency and there was a negative frequency. How that negative frequency looks like? Negative frequency also is having just this representation minus some, or means minus of j 2 pi f0 nt plus theta n. Okay. So, it also has that concept of theta n, but whenever we are giving the rotation, it is actually, if we have to trace back, it is rotating in the other direction. So, this is rotating in the positive direction, whereas as we increase this theta, basically it will be, if I see in the cosinusoidal, it is actually initially first it will be increasing as I basically increase this t, whereas here if I increase t, I will see that there will be a reduction. So, basically if it rotates on this side, the other one is rotating on this side. Okay. So, these two phasor, just the positive one is representing a rotating phasor which is rotating in anti-clockwise direction, right, and the negative phasor is something which is rotating in the clockwise direction, right. So, the negative frequency actually means these two phasor, and the means clockwise rotating phasor gives me the negative frequency. And what is eventually happening, if you see why the signal is becoming real, I have this representation. Now, if you are interested, what you can do, you can start putting this positive phasor and trace this signal, imaginary signal. And if you represent this rotating one, which is clockwise rotating, and if you also trace these two signal, add these two up with respect to time. Every time instance you take those values and add them. What eventually you will see that this thing will get cancelled out. So, in the imaginary axis, if you add these two, you will get nothing, it will be always 0. For every value of t, it will be 0. And in the real axis, for every value of t, we will be getting a different cosinusoidal. Okay. The cosinusoidal we were producing. This is exactly what is happening. So, that means my cosinusoidal, I can actually have a equivalent representation. It is just mathematical equivalence. A equivalent representation where I can say that it is just a addition of two phasor rotating clockwise and counterclockwise, and that counterclockwise is actually the positive frequency and clockwise one is the negative frequency. If I just take these two things and then plot the frequency domain representation, that gives me, due to exponential Fourier series, whatever representation we get. So, and in that the frequency is just this, which is in terms of this complex rotating phasor frequency or that phasor rotation frequency, angular rotation, okay, that the phasor has. Okay. And that is why, because there are two counter rotating phasors, so I have automatically I am getting a concept of plus and minus. A general sinusoidal does not have this direction, because general sinusoidal is just represented with respect to omega 0, right. We just write sine some 2 pi f0 nt, right. So, it is just having a frequency, I do not have a concept of negative frequency, whereas whenever we start representing it in the complex domain, then we get a representation, because there is a direction of rotation. The phasor generates sinusoidal, but it actually generates due to its rotation in which direction. Different direction generates different kind of complex components. Okay. So, that is in a nutshell, that is the that is the realization of negative frequency, why negative frequency comes, and we have already seen that these two are equivalent representation. Here in phasor also you could immediately realize that it is nothing but a real one. If I take these counter rotating phasors, the imaginary part gets cancelled out. You can just trace them in time, add them, you will see that they get vanished. Okay, they will just negate each other, and you will see that it's getting cancelled out. Whereas the cosinusoidal one, there will be a real part, and that is actually the signal you are getting. Okay. So, any real signal, it must have a equivalent phasor rotating phasor representation, and because the rotating phasor representation has direction, so that is why we are getting this positive and negative frequency concept. So, it is just a concept as long as we are representing it in exponential. So, you might be asking, why do I need then the exponential representation? That might be a natural question, that we have a equivalent trigonometric representation already. The exponential one is actually giving me that trigonometric representation only, whereas the exponential one is actually a complex one which is originally not existent. However, my this one, the actual cosinusoidal representation, that is real one, those are the signal which exist. So, why we are actually looking for this exponential representation? The reason is that in the trigonometric representation you have a sinusoidal as well as a cosinusoidal representation, okay, which is double representation, and they have different coefficient. Okay. Instead of that, if I do just exponential representation, yes, I get complex number Cn, but I get a unique thing. Okay. Of course, you know that every Cn has two components, the amplitude as well as spectrum, but amplitude as well as the phase. But we know that if I just interpret it in complex domain, it is just a unique representation Cn. I don't need two An and Bn, it is just Cn. Okay. So that is the utility of representing it in exponential Fourier series. And you will later on see that exponential Fourier series also aids you towards realizing another thing where any signal can be represented, that is called the Fourier transform. We will next, probably not in this class, we will try to appreciate what happens when we try to represent any signal, not just periodic signal. With Fourier series we have only represented periodic signal. Later on we will try to see that if we have any non-periodic signal also, that can be represented, and there you will see that exponential Fourier series becomes extremely helpful, because that gets extended towards the Fourier transform. Okay. So with this, maybe we can give two very important examples. So let us see the first example. Okay. So in the first example, what we are trying to do, we are actually just whatever we have learned, we are trying to apply them. Okay. So we have a signal. This is something I have already given you. Now we are just trying to solve that. So this signal is something like this. It has a period of 2 pi, and it is represented as this. Okay, so this is pi, this is 2 pi. So after every 2 pi it gets repeated, same in the negative also. So at minus 2 pi, so basically this is eventually minus pi by 2, this is pi by 2, this amplitude value is 1. So this is my GT if you just take. Okay. So all I want to do is, I wish to see how this signal can be decomposed into known signals. Okay. So what we have to do, we have to evaluate first, let us say D0. Okay. So D0 is nothing but 1 by T0 integration. Now I have to do it over a period, that should be minus pi to plus pi, that can be one period, it is 2 pi, because this thing gets repeated at every 2 pi. Okay, so minus pi to plus pi, I have to put the signal itself, okay, so which is omega t into e to the power minus j 2 pi f0 n t. Okay. So what is f0? f0 is 1 by t0, and t0 is just 2 pi, so 1 by 2 pi, right. So this is what we get. Now evaluate this integration. So all we have to do is evaluate this, means actually Fourier series we are trying to evaluate. So if you evaluate this integration, what do we get? See, minus pi to pi minus pi by 2, it's not, it's 0 actually. So whatever happens, integration in that period will be 0, and minus plus pi by 2 to pi, it's 0. So it is only defined between minus pi by 2 to plus pi by 2, and the value is 1, right. So it is just e to the power minus j so just do the integration, it should be t0 minus j 2 pi f0 n and e to the power minus j 2 pi f0 n. So we have to put the limit, so 1 will be pi by 2 minus right again minus pi by 2, right. So, minus pi by 2 become plus. Right. So, this is all that we get. Now, you know that f0 is 1 by 2 pi. So, this is actually becoming 2 pi f0, that becomes 1. So, this entire part you can put as 1, this entire part you can put as 1. Okay. So, 1 by t0 . Okay. Wait a second, what do I do? Oh, I am evaluating dn actually, right, because at d0 it should be already n equal to 0. So, it becomes just 1. So, if I just evaluate d0, it should be again 1 by t0, integration from minus pi by 2 to plus pi by 2 only defined, and omega t becomes 1, that is all right, but this becomes 1 already. So, it should be 1 dt. Okay. So, this becomes pi divided by t0 is 2 pi. So, this becomes half. So, d0 is half already. Okay, this one. So, how much we get? It is e to the power j, e to the power minus j n pi by 2 minus e to the power j n pi by 2, right. This is fine. Okay. So, now all we have to, there is a minus. So, this is just again put Euler's theorem. We will be immediately seeing that the j part gets cancelled and this becomes minus 2 cos, right. Sorry, minus 2, no, the j part is actually, because it is minus. So, the j part will be there. So, it will be minus 2j sin inside part, right. So, it becomes minus 2j sin n pi by 2, okay. And then again you have this becomes 1, t0 is 2 pi, and so basically you have minus j is already there, which gets cancelled, t0 is 2 pi and n, right. So, 2 gets cancelled. So, you have sin n pi by 2 divided by n pi. So, this is our answer, right. Eventually, if you plot, it is actually almost like a sin x by x kind of thing. So, I can put this as by 2 and I can multiply into 2 half, right. So, it is just half sin sinc function or sin c function, right. So, what is happening if I just plot it? It is a sinc function. At d0 it is half, and then it just goes to again 0 at 2, goes to again 0 at 4, and so on, right, 6. So, it just comes down like this, goes up, same thing happens over here. That is the envelope, of course, and at every value this is 0. Okay. So, this is the plot, we get d0 and corresponding dn. Do we have a phase over here? We do not, right, because you have seen that all dn, it is no longer complex. So, they are all real values. So, basically the phase plot will be all 0, it does not have any phase plot, just amplitude plot. What eventually is happening, that these sinusoidal are getting mixed, right. A sinusoidal, first a DC term of half. So, basically if you just take a signal of strength half. Okay. Next, a sinusoidal of period 1, sorry, period that 2 pi, okay, and the amplitude is at this point probably the amplitude will be 1 by pi. So, with 1 by pi and period that 2 pi, if you just put a sinusoidal, sorry, it should not be a cos, it is means it should be, see the phase part is not there, it is a real part. So, it must be the cos part, right. So, it is the cos part and the amplitude is 1 by pi. So, basically what is happening like this, you keep, so the second one which is 2 into 2 pi, okay, that is not there, that is not present. So, that coefficient is 0. So, you keep putting all those sinusoidal, you add them together, you will see that the same signal is being generated as long as the coefficients are right. If the coefficients are not right, they will probably not reproduce the same signal. So, this is what exactly is happening. So, any signal, if you do Fourier analysis, it will give you corresponding sinusoidal, okay, nothing else. The next sinusoidal, probably the next one will not be there, but the next to next one, that is a thrice the frequency. So, it should be repeated. Here the sinusoidal is repeating within this period only once, okay. So, it should be repeating thrice within this period with a amplitude of this much. If you just put that and you keep adding those, all those sinusoidal up to infinity, you will see your signal is getting represented, okay. So, this is what exactly happens in Fourier. Why we have done that, we will see that later. This is a typical example which will be required, but next we will be doing a particular means analysis for a particular signal which is immensely important. You will see the sampling theorem is based on this particular Fourier series representation. We will come back to that, but before doing that, we need to understand something called a Dirac delta function. So, we will try to first define what do we mean by Dirac delta function. So, Dirac delta function by definition it is like this, is defined, it was of course defined by Dirac and it is on his name. So, delta t is having a value 0 as long as t is not equal to 0, that is the definition of a Dirac delta function, okay. It has some more definition, we will come back to that later, okay. So, the definition is that other than 0, it is 0 everywhere. It is just at 0, it is almost undefined, it can take very huge value, okay. Equivalent representation of delta t is something like this. It is a box function, okay, defined from minus epsilon by 2 to plus epsilon by 2. And the strength of the box is 1 by epsilon, okay. So, what does this mean? This will become delta, or this will approach to delta, Dirac delta, the way we have defined it, if epsilon tends to 0. So, what will happen? As epsilon tends to 0, the separation will be this is the box function. So, it is 0 everywhere. As epsilon becomes 0 and 0, so all other values it will have eventually 0, only at value 0 it has value 1 by epsilon, epsilon tends to 0. So, this goes towards infinity, right. So, it happens to take the position of delta t, okay. So, this is one typical example of delta function, and whenever you give this definition, it has a added valuation. Think about this thing from this definition. If I integrate delta t from minus infinity to plus infinity, according to our definition it is a box function. So, it should be area under this box, all other places it is 0. So, this area is 1, so this must be 1. So, that is the added thing, added definition of delta t. So, delta t must be defined with respect to this and this one should be added, okay, which almost takes delta t towards that box function. If these two definitions are the definition of delta t, then I can give a definition of delta t in this manner, where I have to put an additional condition that epsilon tends to 0. Okay. So, this is in a way our definition of delta t. Now, let us try to see some property of this delta t. Okay. So, suppose I have a function, let us say x t. I multiply this function with delta t. Okay. What do I get? So, what is happening? X t might be having any value. Think about that box definition of delta t. So, at t equal to 0, it has around t equal to 0, it has this definition, right, minus epsilon by 2 to epsilon by 2, and it is 1 by epsilon, right. So, now what will be the value of this? It will actually means this value can only be realized if I start first integrating it. Okay. Let us say if I can integrate this thing. Why I am doing that? Because delta t integrated fashion, it has some definition, right. So, if I integrate it, now what is happening? On top of this, I am putting this definition that epsilon tends to 0. Okay. So, if epsilon is tending towards 0, so what do I get when I integrate? As epsilon becomes 0, I have this function is there, this function at x0 has some value. Okay. If the epsilon is very small and infinitesimally small, then x0 around that will almost not be varying, as long as it is a band limited signal. That means it is not changing arbitrarily, that this point immediately next point it can go to anywhere. As long as it is a continuous differentiable analytic function with all those nice property, then I know that very small epsilon, it cannot change, it cannot deviate. So, it will be, as long as my epsilon is very small, within this minus epsilon 2 by 2 to plus epsilon by 2, it will be always taking value x0. Okay. So, what I can do? I can write that it will be taking x0 value. So, it should be, so everywhere it is taking x0 value, and this integration has to be done from minus epsilon by 2 to plus epsilon by 2. Okay. And within this, what is the value of delta t? That is 1 by epsilon. So, this should be the integration. X0 is now a constant, because I have already said that if epsilon is sufficiently small, x0 is not, means xt is not varying around that value. Okay. So, x0 goes out and again I get 1. So, what is eventually happening? Whenever I multiply a particular function with delta t, and if I integrate it, I will be getting that particular value back at that point. So, the functional value at that point I will be getting back. This is called the sampling property of delta t. So, basically whenever I multiply a function with delta t and integrate it, it will just sample out the value where delta t is defined. Okay. So, whenever I say delta t, it is defined at 0. Whenever I say delta t minus capital T, it is defined at t equal to, because this has to be 0. So, it is defined at t equal to capital T. So, at capital T, whatever the value of that function, it will just take out that value. So, this is why delta has a very nice property mathematically, that it picks up the sample value at that point wherever that delta is defined. Rest of the values, it will just make it 0. Okay. So, this is a very important property of delta, and this is some property which will be heavily using, especially you will see the entire sampling theorem is based on this particular understanding of delta. Okay. So, what we will do in the next class, that we will try to exploit this particular sampling condition and some other property of delta to get a comprehensive understanding of a particular signal. So, this is something we will do next.